Yeah, this one. Hey everyone, I'm Shehab. I'm the co-founder and CEO of LakeSail. We're and co-creator of Sail, and today we're going to do a high-level overview of the internals of Sail. So with Sail, we wanted to unify data and AI workloads. With traditional data engines, Python runs out of process, which means you have to cross an expensive IPC boundary, which makes AI integration structurally limiting. And so kind of the thesis we came to was you need to rebuild the engine. You can't just accelerate it. So, with Spark and other JVM-based engines, if you want to accelerate the engine, you still have to deal with the JVM runtime. Python still runs out of process for the most part, and you kind of have bolted on control in many scenarios. What Sail changes when rebuilding Spark and Rust, so we have one Rust native runtime for data and AI. So it's Arrow and Data Fusion based, end to end with Python built in process. So everyone here knows this. Why does Spark hit a ceiling with AI? You have a legacy JVM runtime, right? So Python runs out of process. You have garbage collection, cluster startup, and heap tuning taxing every query. AI leaves the engine, so you're going out of process. You have Serde on every batch, and the JVM doesn't have great, low-level access to hardware. So the workaround ends up becoming the architecture. Right? You have Spark on Ray, Ray on Spark, and you end up having a Frankenstein-like architecture. You have to stitch together these disparate workloads. So what is Sail? Sail is a distributed multimodal lakehouse engine. We unify batch processing, stream processing, compute-intensive AI workloads, and ad hoc workloads. We were the first ones to take the Spark Connect protocol and take those protocol buffers to rebuild a Spark server in Rust. We have two deployment modes, single node, which is great for small data or local testing or simpler ops, as well as cluster mode, which is Kubernetes. And all you have to do is just switch the host URL, and you can, migrate all your Spark code and run on a Rust native engine. So if you want to accelerate the JVM, you're using Photon, Comet, Gluten, VLOX, Oron. Nothing wrong with them. There's plenty of valid use cases, especially when you want to, when you have strict requirements for making sure you are Spark, right? Then an accelerator is very good at making sure you are Spark. But you intercept the physical plan and you offload operators to native code. Photon's column-based, but Spark's row-based, right? So you kind of have this interesting columnar to row tax. And then you're JVM trapped. And so if you want to run Python, you're doing Serde in every batch and out of process execution, right? With Sail, we have a Rust native engine, end-to-end on Arrow. Sail's columnar throughout, so there's no columnar to row attacks. And it's Rust native, right? So no Serde, Python runs in process, zero copy execution. So how did we rebuild Spark Rust? Spark Connect protocol is just gRPC and protocol buffers. So you can take that same protocol contract and substitute in the server. Stack under the hood, so Spark Connect API, custom SQL parser, using parser combinators, Apache Arrow and Data Fusion, and PyO3 for embedded Python, and then Tokyo for an async actor runtime. So if you want to compare Python UDFs in Spark versus Sail, in Spark, you serialize the batch in the JVM, ship to a separate Python worker, deserialize into Python objects, execute the UDF, reserialize the result back, ship back, deserialize in JVM. And I think you can see how structurally limiting that is. In Sail, the engine reaches the UDF node, Python's invoked inline on the Arrow batch, and you have zero copy execution. So why does Python decide AI performance? I mean, any AI workloads in Python. If you're doing feature engineering, embeddings, inference, multimodal physical AI, whatever it is, you're very likely using Python for your feature development. And so it's really important for that Python path to be fast. So, in 2026, most organizations are outgrowing Spark. Spark is 17 years old at this point. And a good example that I like to highlight is at Rednote. They're China's Instagram. They have 400 million monthly active users, and they're doing petabytes of multimodal video processing. And so they had a scenario where they needed to use a Python UDF and process a single 2 gigabyte multimodal video record. Tried it in Spark, didn't work. Tried all accelerators, didn't work. They couldn't get it to run. Sail worked out of box. and now they're migrating their biggest petabyte scale workloads to Sail. So we're going to go in Sail's distributed processing architecture now. We do the actor model, the single-threaded event loop. The architecture is very similar to Flink's. So we have a driver actor with a worker pool and worker managers, which manage worker state for the request. Our workers are stateless broadly. There's a job scheduler, which manages a job graph and job state for the request, and then a task assigner. So what's the actor model? The actor model follows the ethos of the Go programming language, right? It's concurrency without locks. Don't communicate by sharing memory, share memory by communicating. Single-threaded event loops, so you're able to have no locks, no contention. And we built it by hand in Rust. There was an Apache, Akka or Apache Pekka, or whatever it's called now. And then our workers are stateless and replaceable. And so they can scale to 0, and server starts up in less than a second. So what's a job graph, right? It's a DAG of stages, and they're partitioned, allowing for parallel execution. You have a job, that's the top level unit of work. You have a stage, that's a fragment of execution. You have a task that processes a single partition of data within a stage. Then you have attempts. So every task can be attempted multiple times. The driver manages the job graph, and the workers execute tasks. So a task region set of tasks across stages. It's the unit for scheduling and failure recovery. A scheduling unit, right? So tasks within a region are scheduled together and retried. And then we have 2 shuffle modes. We have a unified shuffle architecture. So pipeline shuffle, it's streaming shuffle, right? We do it via Arrow IPC, and data flows through local streams within the region. Blocking shuffle, we do object storage-based blocking shuffle. And so boundaries between task regions correspond to blocking shuffles. It's very similar to Ray's blocking shuffle or exo shuffle paper. So task law and resource management is, if you worked with Flink, then this will look very familiar with you, or look very familiar to you. So slot sharing, tasks from different stages, they can, within the same task region, they can share a slot. Distributed query planning. So this is data fusion code, and the goal is you want to break down the execution plan tree into distributed stages with proper input from reading, proper input reading behaviors. So the producer, they're going to wrap the actual input with a shuffle write exec. The consumer, they're going to ensure that execute still works when input is replaced by shuffle read exec. So the input modes that we have for distributed execution, we have shuffle, which we just talked about. So output partition P fetches channel P for input partitions. We have forward. It's needed when you want to go from driver to worker tasks. Broadcast, each partition fetches all input partitions. You wouldn't use it for left out or join. Then we have merge. Single output partition fetches all input partitions. Oops. So, we have one architecture but 2 shuffle modes, and we have a unified shuffle architecture for streaming shuffle and blocking shuffle. We have exchange mode, which is how partitions map from producers to consumers. And we have output mode, where our output streams downstream or persist first. Task regions are the payoff, right? So pipeline edges keep stages in one region, and they're scheduled and retried together. Blocking edges will actually cut the graph, and each side becomes its own region. Pipeline shuffle, so you have partition streams between stages and memory. You have one task region, nothing's persisted, right? So it's really good if you have a lot of sensitivity to latency, or if you're certain that your data can fit in memory, or if the cost of retrying is not expensive. It's all at once, and so it has coupled failure, which means that everything will need to be retried if there is a failure within the region. Blocking shuffle, so we use the no-op reducer trick. And an auxiliary no-op reducer stage makes shuffle exchange durable. So it's still a shuffle exchange. Mappers connect to the no-op reducer stage with the ordinary shuffle exchange mode, and then you merge inside the reader. You persist to object storage, and so you have output is marked blocking. And the interesting thing about persisting to object storage is with Spark or Flink, if you have failure on a worker, then that data is lost, right? But if you have failure on a worker in Sail, out of memory, or whatever, that data is in object storage, and so it's a lot more resilient. So we do push-based shuffle. It's the same concept as the magnet idea in the magnet paper. It's also discussed in XO shuffle and in race paper. And so if you have naive pull-based shuffle, you have 1,000 mappers and 1,000 partitions. That's 1,000,000 objects, right? If you're using Sail's no-op reducer, which is the same concept in the magnet idea or XO shuffle paper, mappers chunks merge into one object per reduced partition. So if you have 1,000 mappers and 1,000 partitions, that's 1,000 objects. You have one stream per reducer partition, right? So sequential reads at object storage, friendly sizes. So what is object storage shuffle value, right? Persistence is not always overhead. It's resiliency, elasticity, and smaller clusters. You can have retries without cascading failures. And so a task rereads its input from object storage. Upstream readers never need to rerun. So there's no cascading retries. You're able to do big jobs in a lot smaller clusters. So only one task region needs to run at a time, while with streaming shuffle, all task regions need to run at all times. And so if you have a really large data set or you just need cheaper computation, you're able to do that. You're able to do that with blocking shuffle. And sometimes the write pays for itself, right? Persistence will add write overhead, but under preemption or memory pressure, it can sometimes cut total job runtime if your data set is large enough. So when should you use pipeline and blocking shuffle? Reach for pipeline shuffle if the job fits the cluster comfortably, workers are stable and retries are rare, or cheap. And latency matters. So if you're doing interactive work or ad hoc work or real-time work, then you likely need pipeline shuffle. Reach for blocking shuffle when workers get preempted, you have spot capacity or churn, memory's tight, or the job's wider than the cluster, or you have long jobs where cascading retries are expensive. Next, we're going to go into lakehouse formats. So, so you have listing tables and lakehouse tables. So listing tables, you have a directory layout, doing nothing. You have a directory layout for your data files to read. After writing, you do nothing. Lakehouse tables, you have a manifest, as your data files to read. After writing, you do have actions. So you have to update your manifest files. Complex DML is largely not supported in listing tables, but with lakehouse tables, they are supported. And then statistics. So with listing tables, statistics are stored in the Parquet file. Lakehouse formats, statistics are stored in manifest files. Schemas inferred from data files for listing tables, while schemas inferred from manifest files for lakehouse tables. Same thing, partitioning is inferred from directory layout for listing tables, and then for lakehouse tables, it's for manifest files. So we built Delta Lake and Iceberg directly in the engine. With Delta Lake, we have full read and write support, conditional delete support, and merge support. We tackled merge before updating because merge is harder to do, so we wanted to inform our architecture. With Iceberg, we have full read and write support, merge support, and delete support coming soon. We have a Duck Lake draft PR that's been sitting around for a year. We'll maybe get to it one day. So Sail's Delta Lake journey. When I last presented at the last Data Fusion meetup, we added Delta RS and Delta Kernel RS, and then we removed Delta RS, but we're still in Delta Kernel RS. Today, we no longer use Delta RS or Delta Kernel RS, and as we came to understand Lakehouse formats, we realized it required really deep integration within the engine. And so that's why we removed those dependencies. So now we have full control of physical plans for DML, and we're able to support, for example, a Delta log scan. So I'm gonna skip these two. Here, you're looking at a very high level and simplified physical plan for merge, and we're able to define these in data fusion primitives. So it's just, a regular physical plant node. The key takeaways we learned from Lakehouse formats is metadata is data, scalable processing is required. Having modular plan nodes, because there's a lot of duplication across Delta Lake and Iceberg, is really important. And optimizer integration is really important as well. Next, we're going to Sail's catalog interface. So we built a catalog interface by hand purely due to necessity with having Spark compatibility. So we don't use Data Fusion's catalog interface. It has an async interface, and it's very focused on catalog objects. And so query planning is kept separate. And so if we're going to compare Sail and Data Fusion's catalog interface is really designed for performance. And that's why there's no async interface. At least there was no async interface when we wrote sales catalog interface. If that changed, let me know. And but sales catalog interface does have an async interface. And so the implementation effort on our end is a lot lower because performance is not our focus for the catalog interface. While in data fusion, query planning is involved, and so there's really heavy integration. So if you've ever worked with Postgres or MySQL and you're familiar with the concept of a system catalog, which tells you the internal state of how your engine's running, we saw that missing in Spark and other data engines, and so we thought, why not bring it to Sail? So we have a system catalog, which is our response to a Spark history server. It's open telemetry based, and so you can do a bunch of really fancy stuff with it, like sending it off to Datadog if you want, which you can't do that with Spark. And we have these tables. So sessions, tasks, jobs, workers, stages. It tells you all of the internals of your engine. And fun fact, we actually use the system catalog in efforts of developing our distributed processing architecture. So it's just a regular table schema. It's a table backed by a logical plan table scan and with a custom table source. It just planned as an execution plan for physical execution. We use execution plan execute from data fusion. So you send a message, and the message context have the table name, whatever metadata, and then you await results. There's no locks or contention thanks to the single threaded event loop and the actor model. So, all of us are here building data engines or adjacent in Rust, but the ecosystem is really important, right? And our goal here should be building ecosystems together so that we can really support production workloads. And so one partner that I want to highlight is our partners at LaserData, Kranti, who's the CEO over there. So, if Sail rebuilt Spark and Rust, Apache Iggy didn't rebuild Kafka and Rust, but made a way better, streaming engine. And so with legacy Kafka architecture, you have that same JVM overhead. You have that tail latency risk, and you have complex operations. But Apache Iggy, which is really impressive, Rust native runtime, predictable latency, right? So P99, you're getting predictable latency. And it's using modern protocols. Kafka is an ancient, very ancient engine. So what can you do when you bring streaming to Rust? You can do millions of messages per second per node, which is pretty wild if you ever worked with Kafka. Having predictable tail end latencies is really important, right? 1 millisecond average write latency is a hard thing to do with Kafka. And so, a really important piece when we're all building is to think about how can we replace the old stack. So if you've used Kafka with Spark or Flink, we can use Iggy with Sail, right? And now you can do streaming ingestion at much bigger scales, with much simpler ops. So if you want to see how that looks like, it would be the same exact thing as if you're using Kafka with Spark. Ingestion is with Iggy, compute happens with Sail, and you do output. Your output's curable results, right? And so what you can do with this is real-time analytics, or streaming ETL, or feature pipelines, or AI enrichments. Let's say, for example, you want to calculate embeddings and do a real-time personalized search or a real-time personalization feed, right? We're going to require you to do ingestion from your database, process that in real time, calculate the embeddings, and output that somewhere. That's really hard to do with a JVM stack, especially when Python becomes involved. So with that, I end it with stop tuning the JVM and replace it. Thank you, everyone.